my name is Zhenming Wang. I am head of the Geological Hazard Section of Kentucky Geological Survey at the UK. And my presentation here is a project we did for the KRCE for the Paducah Gas Diffusion Plant. The title here is Seismicity and Monitoring in the Vicinity of the Paducah Gas Diffusion Plant. This is really a phase 2 project. And my co-PI is Ed Woolery. He is professor over Department of Earth and Environmental Science, also at the UK. So here's my outline. First, I'll briefly give you what objective for this project. And the second, I will talk about seismic monitoring around a particular gas diffusion plant. And the third, we'll focus on central U.S. Seismic Observatory. And finally, I will summarize what we learned from this project. And here is the map showing you the seismicity in the central U.S. If you look at the map here, particularly there are 3 red dots. During December 1811 to February 1812, during a 3-month period, there was a many large earthquake. At least 3 large earthquakes with magnitude greater than 7 occurred during that 3-month period. That's where historically large earthquake affected a large area in the central U.S. And if you look here with Paducah Gas Diffusion Plant, here's Paducah, and Paducah Gas Diffusion Plant just west of Paducah. And you see here very close to the pneumatic seismic zone. And also, if you look around Paducah Gas Diffusion Plant, also has some earthquake there. So that the reason have some concern in terms of earthquake safety. This is seismic hazard map produced by the United States Geological Survey. If you look at this map is the peak ground acceleration with the so-called 2% probability accident in 50 years. And if you look at the value here, here is the pneumatic seismic zone. Paducah is right here. And if you look at value, it's very high compared to West Coast, California right here. Actually, if you really compare the value, pneumatic seismic zone have higher value than California. Think about for a moment. In this country, if we talk about earthquake, everybody will say, well, it's over California. But this is the map produced by federal agency. Put high hazard in New Mexico than California. So that's where is a problem coming for us. This is a design ground motion. Right now, this in all the federal regulation. I just put a parallel that for comparison purpose. Left side here is California, particularly San Francisco right here. Right side is a pneumatic seismic zone. You see here is a Paducah. And Memphis is down here. So if you look at just in terms of value, the highest value is in the pneumatic. You see 300% of gravity, 3G. But California, the highest value is 200%, basically 2G. So in terms of engineering design consideration, in the pneumatic seismic zone, we had to do more than anywhere in California. So this will create problem for Paducah Gas Diffusion Plant or the related engineering design. So this way is a problem coming. And this is a residential building code. So if you look at this, again, this look is overall, this whole continent U.S. I just blow up here compared to pneumatic seismic zone here, and here's Paducah, and here is San Francisco Bay Area. And Paducah, in terms of residential building design, Paducah is in E zone. If you look at E, is the highest residential building design. But San Francisco is a D2 zone. It's lower, one category lower than Paducah. So basically, not anything DOE want to do anything in terms of engineering, design, the earthquake, always a problem there. So this really created a problem for the Paducah Gas Defense Plan, and also problem for Western Kentucky. You can imagine all the impact for the economic development. Now look is one of very specific. That's why the DOE gave us money to do this research. One of key issue back to a decade ago, that's year 2001. If you look this table here, very specific at landfill. DOE proposed to build a landfill at the Paducah Gas Defense Plan for this environmental cleanup. And original DOE design is for 0.4 G, basically 40% gravity for the design. By the year 2001, DOE wanted to make it a proposal, but at that time, UAG has already produced the map. And based on the map, here you see DOE had to design a value is about 0.7 or 0.8. That's where our state EPA demand DOE design for 0.8 G. So original proposal is 0.4 G. After the UAG had produced the map, probably that become a federal regulation, kind of all the federal facility had to consider. So now DOE say, well, this is what they had to design. And again, 0.8 G design is way high. Right now in this country, no landfill design such high. In California, highest design is 0.4 G. So this really created a problem for DOE. At that time, I think year 2001, year 2002, DOE actually challenged our state EPA to the core to want to ask state to issue permit to that DOE to build the landfill. But this another federal agency, they say, hey, look, this is their estimate. So it become a very difficult issue. Actually, I attended a meeting year 2001 and June 30th in Frankfurt. One side is the DOE people, and the other side is our environmental agency people. They are almost fist fight over this 0.4 over 0.8 G. So that's why the DOE willing to give us to support this whole research with this KRCE through the earmark money to look into it. So that's where by the year 2003, the DOE they get the money lead to the phase one, the research. So we part of that, try to deal with, can we do something with it? So I will come back to where after 10 years, what happened 10 years later. So right now, that's reason this project started. One of the key reasons this project started. So the objective for this key research is how can we do something with this extremely high design ground motion. And this is phase one project that started year 2003 and year 2006. One of our main objectives doing the research, looking into hazard assessment, looking at scientific information and what we find. So actually we end up has a report, look into, and then we identify some issue, and we help actually work with state agency, work with DOE, and then we resolve that 10 years later. So I will come back to that later. for seismic hazard assessment, one of the key problems is we just don't have enough data. The early day, in earthquake in the central U.S., really few people pay attention. There's no instrumentation. So if you don't have enough data, a lot of time, humans have tendency to add uncertainty. Make it more subjects guessing. So they add another dimension to the assessment. So we propose to put a temporary network to surround the Paducah Gas Development Plant. And also, because in Paducah, the site also have about 100 meters soft soil. A lot of time, we know soft soil could get additional problem because when earthquake occur, the soil could amplify or de-amplify the ground shaking. So we also need look into that. So that's another facility at the instrumentation we propose to put in there. So we propose to drill a hole, and this hole is almost 2,000 feet hole. So this is kind of phase 1 project. We finished a report, 2008 report. So phase 1. So here just kind of, let me show you very quick phase 1, the main key finding from phase 1. I think it's key thing where we identify in the central, particularly in the Paducah area, we just don't have enough data. So anything, the scientific information is a lot uncertainty in there. A lot of time, just more a guessing. Clearly, this one issue, if you're not careful, you're just compounding the uncertainty. They give you higher and higher estimate. So that's kind of where we identified that. And then we say, well, because the methodology they're using is just using a different model of try to capture the uncertainty. Again, model is just a model after model. Basically, you're compounding the uncertainties. What end up is higher and higher. So that's where we see why you have such high the ground motion estimate for the pneumatic and for the Paducah Gas Development Plant. So we identified that. We just said, well, can we just use the common sense approach? We know all these estimates have uncertainty. It's large uncertainty. But common sense approach, we always say, okay, if large uncertainty, we just, okay, look at what the mean or median or certain percentile, where is this value? What the range of those? So that's our recommendation. So in terms of methodology, they begin federal and they all use so-called PSHA, probability seismic hazard assessment. It's just a probability model compounding uncertainty. But we recommend we should look at scenario, individual earthquake, and look at where's the mean, where's the median, and what range we know, and then we can make a proper recommendation. That's our the recommendation. So now, after 10 years, we done this study, so we was able to persuade DOE and our EPA people. The final approval is 0.33 G. So after a decade's effort, they started 0.4, but everybody accept very happy with 0.33 G. So clearly our research helped solve the issue. Again, it's more than just landfill now. Again, this is now DOE they can use for any facility, any other engineering design at the Paducah Gas Development Plant, they can use it. And I think also a larger impact for the area, we was able to revise like a building code and residential code for Kentucky. Like also the transportation cabinet use our recommendation right now for bridge design. So I think our research not only help DOE, our state regulator, resolve the landfill design and engineering design for the Paducah Gas Development Plant, we also, our result also help Kentucky resolve other issues, help there is economic development for the Western Kentucky. So that's phase 1 was very good. We are very happy with that. And so this is kind of phase 1 research. And then really phase 2, I think we talk about today is really phase 2. Phase 2 really, they started year 2009. That's kind of where's the money coming. I think it's phase 2 still ongoing, but we did not get any money after 2012. Really try to focus on 2 things. Continue to monitor the seismicity in the particular gas division plant surrounding area and complete that deep hole instrumentation. And here I've just show you where's our network. And in Kentucky, we run a seismic and strong motion network. And really, you see here most focus western Kentucky because this where is the pneumatic seismic zone is. And very specifically, you can see here the square dot here. This is temporary network we propose to put in the surrounding particular area. We started year 2003 and all the way through 2012. That's we continue doing that. And also you can see the circle, and there's 2 very particular gas division plant. We have a station there called VSAP. That also is borehole. We put the strong motion on surface, also in the bedrock. Again, the purpose try to understand when the ground motion coming, what the bedrock shaking and the surface shaking. So we want to understand that. And then very specific is a so-called QSOs right down here. And that is about almost a 2,000 feet hole. And we drill several hole here. One is 100 feet, the other one is 850 feet, and the deepest one is 1950 feet. The purpose for the seismicity monitoring, again, this is UAGS, how they project where is earthquake could occur, the fall basically. If you look here, this is year 2002 version of UAGS. UAGS update their seismic hazard assessment every 6 years. So this is year 2002 version of their update. So if you look that they draw the fall, this is where earthquake occur. So particularly right here, so they kind of draw the fall right to the doorstep of particular gas division plant. Again, this is more arbitrary, and they put a line there. But in terms of hazard assessment, if you put a line like this, from engineering point of view, basically say, hey, you cannot do anything. Because you put a fall, like you talk about magnitude 7.5 or even 8 earthquake could occur at the facility. So basically, you're death penalty. You cannot do anything, really. So, and then this is a 2008 version. They draw more, and they put a weight, like, oh, this is 70%, 10%, and 5%. So again, it becomes just probability, arbitrary assigning probability. But what really data tell you? So that's why we want to put a network to see is there seismicity associated with this fall. So one of the keys why we do the monitoring. So if you look here, this during our almost 10-year period, but there's a 2-year, 3-year period. We only see 2 earthquakes in Kentucky territory. One is quite close to particular gas division plant. The other one, right, is along the Mississippi River. But there's more earthquake in the pneumatic zone. So again, this is data. This is observation. But if you take this observation compared to what you are drawing, the clearness is something is not consistent. So that's where we think that's where they just adding uncertainty into the assessment. That's why get higher and higher hazard assessment. So this is what our data show. And this is just one earthquake from our network. And the station is at VKY, and they see here the small earthquake our record show. During the 3 years from year 2009 to the year 2012, we only really get 2 earthquakes in the particular gas division plant area. This is another, the same earthquake recorded at the Paducah Gas Development Plant. That, remember, this is a borehole. This is at the bottom in the rock, and we also have the intermediate in between also record. And this record is not scaled, so you cannot look at a relative. It's kind of water level. I have not done any correction yet, but just show you record from that earthquake. Let me show you the we call Central U.S. Seismic Observatory, and really the hole, this deepest hole is right here. You see here the depth almost 600 meters to 587, and we put a sensor. This is in the bedrock, and also another sensor at the depth here is 526 meters, and then the 260 meter and 30 meter and free survey. So this we have several levels of the sensor. The key thing we want to understand when wave propagation from the bedrock through the soil, what we can see, what we can learn. That's really try to understand if Paducah, there's a strong earthquake occur in the New Magic, what the side this soft soil can do, either to amplify or de-amplify the ground shaking for the facility. And here, this is geophysical law. When we drill a hole, we also have a company to come in to do a geophysical law. And we also geological law. Through these, we will know better what the property of the soil, different kind of soil, of different physical property, and also the shear wave velocity. So we do a series of log. Here's shear wave velocity profile, all the way to the bedrock. Then here, just get an example. This Paducah Gas Development Plant soil profile. The bedrock is about 100 meter kind of horizon, different thicker as soft soil. And this, we also have, I just showed you earlier, there's a record. And we have a bedrock record service. This is the first one we recall this earthquake back to, this earthquake actually is back to 1994. That's way before the project. So first record to show you this bedrock, you can see here, this is already scaled. This bedrock motion, you see, go up, the amplitude start to amplify. But this is for small earthquake. But if you have a larger earthquake, actually, de-amplify. So soil reaction to the ground motion depends on how strong the shaking is. If you have very strong, actually, soil can de-amplify. And if you have weak ground motion, actually amplify. So that's kind of, you got to understand this and to make a proper engineering design. And this is the profile actually right underneath the landfill. When they derive the 0.33 G is based on this analysis. Actually, de-amplification, the input is 0.36. And then they run several earthquakes, and the largest one gets 0.33 G. So that's why everybody agree 0.33 G is a number for the design. But for this facility, it is difficult for us because it's deep. The water pressure is so high. This kind of where, you see, we started the phase 2, the project year 2009, we started put instrumentation down. And as soon as we put down, about a couple months, we start see the problem because our cable design is not strong enough to stand high pressure, really just squeeze it and shook it. So you can see here, we back and forth a couple of times, and I will show you, we do get some good record from small earthquake, also even like Japan earthquake, we also recorded a good record. But it's only during a short period. So right now, this instrument all working, but this one is not working. We still, right now, don't have money to really try to get a good cable to go back. So right now, as of August year 2011, and this Zhenming had pulled it out. So what is stacked right now is all this other is in operation, but this set is not working. Here is kind of give you a chart of the QSO history of instrumentation, when we started to put instrument in and when the problem coming and where right now, and also show you we do have got some data. And we see here we get total right now have 95 earthquake record. And 24 of them is local events, earthquake occur around in the surrounding area, and 37 is from a little bit far away, like Arkansas earthquake. And a third of them is 34 earthquakes occur globally. So we have a pretty good data set. Actually, my co-author, Worry, and I, we just finished a paper ready to submit it for publication, just on this data process. And here just show you where's earthquake, the record where's earthquake occur. It's a local earthquake also in the surrounding area, and regional earthquake is more from Arkansas. I think you may have heard of the called induced earthquake. That earthquake, one of earthquake, had to do with some the fluid injection in Arkansas back to year 2011. And other global earthquake you see from South America and even Japan earthquake, we call that earthquake the larger, that's the year 2011, the Japan earthquake. Here is the record. You see here, this is at a bedrock, this at the surface, and from Japan earthquake. So very sensitive, you can see here, but this is one of this vertical component, almost identical, but if you look horizontal, it's a different. You see the bedrock is almost, you see no motion, but in the surface there's some motion. So this is kind of is a difference. So we can analyze this, can understand how the wave propagates through the soil, what the soil impact for the ground shaking. So this is how we do the study. And this regional earthquake from Arkansas, magnitude 4.7. And you see here different layer at level, this bedrock, just vertical component. The instrument we put on is a 3 component, 2 horizontal, 1 is vertical. So if you look here, this vertical component, this bedrock, and this is another one. So you can see now from the bottom, you can see the amplitude going up. And also, it's you can see the duration also a little bit longer. So you can see this how wave propagate from the to the bedrock to the soil and all the way through the surface. So that's, we can use this data set can understand, how the soil affect on the wave propagation. This is horizontal component, and the same thing you can see here, the bedrock, you start to going up, the amplitude increase. There's another, because of 2 horizontal component. And also, with this kind of data, so you can understand also how different kind of wave propagation, how the reaction, here just giving, because this is a P wave and also S wave, and also maybe a surface wave on here. So different kind of way, how they interact each other. So with this data set, we can understand better all this wave propagate through the soil. So that's kind of give you a good data set to work with. And one other thing you can see here, this edge wave and propagate from the bedrock through the, and also you can see from the surface, reflect back. So that's kind of how work. And then without the data, sometimes we're difficult, but with data, now we can see it. So that's kind of pretty much what I have today. Try to briefly go over the overall project and phase 1 and phase 2. So this kind of what phase 2, the summary, what we done. And clearly from what we see in terms of seismicity show the earthquake occur in a particular area is different from New Madrid. So if you say, if you draw the fault line directly to the particular get-given plane, clearly it's not consistent with the data to us. And the deep hole instrumentation clearly give us some good data to work to get a better understanding the wave propagation through the soil. And our research clearly helped resolve some issue for particular get-given plan, also benefit for the community down there. That's all I have. Thank you.